Well, hello. I'm back again, this time for part 2 of my video sequence on the AC induction motor. And last time we were left off, we were talking about this model for one phase. And what I'd like to do is, and I showed you some values we had for these that were based off an example in the electric machinery reference that I was talking about. But what I'd like to do is actually go through and give you some typical values that I found in another article online. So let's look at that. Okay, so let me make this a little bit bigger. Okay. And by the way, this is from an article Mr. Sean and Mr. C from Applied Intelligent Control, John Wally and Science. Okay, so let's look at motor 1. Now motor 1 here, what we have is a kilowatt rating of 7.5 kilowatts. Now remember that 1 horsepower equals 746 watts. So if we go in and we take this 7.5 kilowatts and we divide it by 746, we end up with about 10 watts. So this is, or 10 horsepower. So this is about a 10 horsepower motor, which is pretty much the motor that we did in the example. You know, we're going to be using throughout this video here from the Kingsley book. And let's look. So it's 10 watts, 220 volts. Okay. Here is stat for the stator. And I assume that's line-to-line voltage. 60 hertz. Rated speed 1160 revolutions per minute. 6-pole motor. Stator resistance 0.282, which is what we had. Leakage reactance 512. Rotor resistance stator, now we had 0.144. A little bit different. XL about that, and XM, so slight differences between there. Notice that what you also have here is a coefficient of friction and also your rotational inertia here of kilograms, and I thought about using that in this video here to figure out, to plot the acceleration versus the rotational speed, but hey, it's already long enough as it is. So anyway, this is a 10 horsepower motor, very similar to what we are using in the others. Now here what we have is a 0.75 kilowatt or 750 watt. So here we have 750 divided by 746. So this is a 1 horsepower motor, 220, 60 hertz. This time we're talking about 4 poles, so it's a slower speed. Now look what's happened to the RS. The RS is higher than what we had before. Before we had an RS of like 0.28, and this time we've got like about 10 times that, and of course it's per phase. The RR is about 2 ohms. Before we had an RR that was what, about 0.1 or so. Let's see what else has changed. The XLs and stuff have changed. Okay, and then let's go over to this one here. So we like 0.147 kilowatts. Okay, and so let's look at that. So 147 divided by 746, and so here we're talking about a fractional horsepower. This is about 0.2 of a horsepower. Okay, and let's look at this. So here we're going to 230 volts as opposed to 220, still 60 hertz, 4 poles. RS is even higher than what we had before. RR is much higher. Different values here. But notice the poles. Let's look at the poles again. This very first one here, we were talking about 6 poles, and we were talking about RPMs about, actually this is, they got R per minute, or revolutions per minute, I assume is what they're doing. So 1160, okay. So this was 6 poles, and what did we say 6 poles was? 6 was about 1/3 of that, so this is about 1800 or 1200, was it? So 1200 would be the synchronous speed, so this is the actual speed going that it's actually going at, so there's some slip there. So that's with 6. This is with 4, so here 1800 would be the synchronous speed, and we're like 1770, and here 1800, so this is a little bit higher. This is also 4, so running a little bit closer, a little bit less slip here. So that's another thing to notice is you got a little bit less slip with this smaller motor than you do with this bigger motor here. 1770 versus 1790. Okay. So anyway, just wanted to kind of show you a couple of values there. Okay. Let's go back into our GIMP here. All right. And let's go to the next page. Okay, so let's see here. All right. So the first thing that I want to do is actually go in and calculate the input impedance here. Now, back in the old days, I've spent many days doing lots and lots of algebra on circuits similar to this, mostly communications applications for filters and matching pads and things like that. And that's the way I started to do this, but after spending a day on this, I realized this is really dumb. There's really smart tools out there like Python, and there's C, and there's all kinds of programming language where you do this. And Python is really way up there as far as a great language to do a lot of stuff like this. Okay, so you don't really need to go in and reduce everything down to something that's real pretty. You can just actually write the equations and then plug it into Python. Also, I showed you some circuits that I'd put in LTSpice, which is another great program to do stuff like that. So anyway, I wanted to calculate the input impedance, and so let's see what I did. So basically what I said was, let's see, what we have is we have RS plus J omega LS, okay, and omega is 2 pi times 60 hertz, okay. And then I've got this parallel combination here, right? So I've got J omega Lm times the sum of this, which is J omega Lr plus R over R. So product over sum, okay? And what I did is, because early on when I was doing some simulations here in Python, I noticed that I was getting divide by 0 error. So I decided to go ahead and try to get rid of this over S as much as I could. Now if you go in and look in the textbooks like electrical machinery and stuff, they really didn't use any tools like I'm using now. They probably weren't there, or if they were too difficult to use, especially for the book. So they wanted to leave it in that form because R over S was a common parameter that you could see, well, okay, it varies as this. But for me, since I'm just plotting and doing some simulations on circuit simulation software like LTSpice and writing my own stuff and Python, I don't really care about that. So what I did is I went in and I basically multiplied this on through, and I multiplied S on the top, S on the bottom. And so when I do that, I end up with this, and then going in, so this is as far as I want to reduce it. much less work than what I have been doing with this. And I made a couple of mistakes before I finally got the final result on that. But here, real easy. Just do a little bit of basic algebra to get it where it's at. I don't even have to rationalize it or anything. Okay, and so what I have here is basically this is the input impedance. And, you know, in the electric machinery textbook that I was telling about that I really liked, they actually included this in the textbook that I actually used for engineering school. They neglected this on the basis that it's a small effect, but another reason why I liked electric machinery is they went ahead and included it. And it turns out in some of the plots I was doing, then it made a difference. Okay, so anyway, there you go. There's the slip. I wrote that down again. And in here, what I'm doing is looking at the different cases here, which is a good thing to do. So let's say that the slip is 0, which can't happen, but we can get close and close to that. So that's where the motor shaft speed is equal to the synchronous speed. Okay, and I say it can't happen unless blah blah blah. Okay, so if s equals 0, then Zn reduces to this, right? So here, R over S approaches infinity, so IR equals 0, no transfer of energy from stator to shaft rotor. So Zn is the Rs plus the magnetizing inductance of the stator windings. So it's high inductive load. So essentially what we said, and we saw this before, is if S is 0, close to synchronous speed, or really at synchronous speed, this is infinite. There's no current flowing through here. So all you have is you have RS, LS, and LM. Okay? So basically, this is going to be mostly an inductive load. Okay? So that's when you're at synchronous speed and no power is being transferred. Okay? The other case is S equals 1. So this is where you have basically the motor's not rotating. Either it's locked or it's not moving because you're just starting it up. So here you have LR, the small leakage, plus RR small in parallel with the large inductance. Okay? And so essentially what you have here is that this is small, this is small, this is big. This is still going to have some current flowing through it, but it's a much different situation than what we had before. You're going to have much more current flowing under this condition here because this is a much smaller impedance than it was before, and so you're going to get a lot of current flowing through here and then some current flowing through there. So that's under the locked rotor or just at startup. Okay. Now let's do some fun stuff here. So let's go in and let's get out of this and let's pull up the Python. Okay, so let's see here. Let's pull this up and let's pull up input impedance. Okay, so here is my Python file, and here are the parameters that are basically being used. This is the 10 horsepower motor, 220 volts line to line, which corresponds to a phase voltage of 127 volts. And like I say, these are values that were used in the example in the electric machinery book. And so here I'm just basically going in, and by the way, I'm using my Matplotlib, and I'm using NumPy that are libraries inside of Python that I'm using for this. Okay, so the first thing I'm doing is I'm basically going in and I'm creating this or calculating the synchronous speed. And so notice that this is a 6-pole device. Okay, and so we have omega s equals 4 times pi times f over p, which is the frequency, the formula I gave you before. So I calculate ws or omega s. The slip, what I'm doing is I'm going in and going through a whole bunch of values. So here I'm just creating a vector of values that I can plot against. Okay, and so I'm starting at a slip of 0.001, going up to a slip of 1. And so 0.001, then that's pretty close to synchronous speed, right? And then 1 is pretty close to, or actually it's a locked rotor condition. And I'm going in steps of 0.001, okay? So slips of 0.001. Okay, now, here, the motor speed is essentially 1 minus s times the synchronous speed, right? And so, and we talked about this before, you know, if your 0.02 is your slip, then essentially this is going to be your actual speed of the motor is going to be 98% of the synchronous speed. Okay, and here what I'm doing is I'm going in and doing the input impedance. Okay, now if you go back and look at those equations, and we will here in a minute, well actually let's do it right now. Bring that back up. Okay, you'll notice that the equation for the input impedance is Rs and Ls, J omega S, plus you have this rational function here. And so what I'm going to do is calculate this and call it A, calculate this and call it B, and so that's what I'm going to plot. Okay, so let's get out of this. Okay, and so that's what I'm doing here is I'm saying A is the numerator part, B is the denominator part, and so the input impedance is Rs plus Js times J, makes that complex, plus A over B. Okay, so this is that function that I calculated, and look, I'm just letting Python do the calculations. No more lengthy algebraic things, you know, and making a mistake here and there and then having to repeat it. This is so much simpler, right? And after all I want to do is just plot it, right? All right, so this is a complex value, and that's another great thing about Python is it's really easy with the libraries NumPy and SciPy to do arrays and complex values and all that kind of stuff. C is my language and C++, but Python is growing on to me really quickly because of all the built-in libraries and stuff. Okay, so Zn, this is the complex input impedance, and what I did was I went through and I essentially went in and calculated the magnitude, and you do that by going in and using the NumPy function ABS of Zn, that gives the magnitude, and then the angle CA is also a function built-in angle of Zn, and degrees true because I wanted this in degrees. Okay, and I also calculated the real part of the input impedance and the imaginary part of the input impedance. And here what I'm doing is just calculating different speeds here. For different slips, so with a slip of 0.02 or 2%, then this is the actual motor speed, okay? Because remember, 1 minus the slip times the synchronous speed gives you the actual speed of the motor. So I actually calculated some constants here for various slips, 2, 3, and 4%. And here what I do is I'm actually going to print out some values. I want to print out the magnitude, the angle, the real and imaginary for various slips. Now, in my vector here, or an array that I created here for S, okay, this is an array of values, and so what I simply have done here is I figured out that the 19th element of the array S, okay, of all these values corresponds to a slip of 0.02. The 29th element corresponds to a slip of 0.03, and the 38th element corresponds to a slip of 0.4. And so then I went through each one of these were functions of the slip and actually impedance, so I can just print out the actual values. Also what I've done is actually gone in and plotted the values. So the first thing I'm going to do is show you the plot for Zm, the magnitude, and Za, the angle of the impedance, okay, versus slip and also the actual motor speed. And then what I'll do is I'll uncomment this out and actually print this out. So let's go in and let's run it. Okay, not too bad. Okay, so first off, let's look at some values here. Okay, so notice for a slip of 0.02 or 2%, the magnitude of the impedance is about this, 6.7. The angle about 32.27 degrees. The real part 5.7. The imaginary about 3.6. If we increase the slip to 0.03, then we got a magnitude of 4.9, CA 26, CR, CI. And if we increase to 4, then we end up with these values here. Okay, now something that I probably haven't said in the other video, this video, is like, how do you change the slip? Well, actually, it's the load that determines the slip. Okay, and when we start talking about torque, we'll talk about it later. You put a heavier load on it, then it's going to slip a little bit more. If you put a lighter load, then it's going to slip less. No load is going to be pretty close to synchronous. A heavy load, then it's going to slip more than it does with a lighter load. So the load on the motor is what determines what the slip is. Okay, and you choose that. You choose the load to operate at a designated slip, and typically like 0.01 to maybe 0.07 for slip values here. This example in the book, though, they use 0.02. Okay, now let's look at this curve. So the angle here is over here. Now these aren't negatives, these are just little tick marks, just like over here. You wouldn't believe how much time I wasted trying to fix a problem that wasn't here, but that happens early in the mornings. Okay, so this is plus 30 degrees, 40, 50, 60, 70, 80, whatever. Okay, so over here, this is at the rotational speed of the motor 0, which means you have a slip of 1. Okay, and here's a slip of 0, which means you're at synchronous speed. Okay, so first starting up, essentially this is going to be the actual impedance that you have when you have a slip of 1. Okay, and as you can see, the magnitude is somewhere around 1, less than 1 ohms here at this point. Okay, and you can see the phase angle here is somewhere around 50 or 60 degrees. So for the magnitude here, it's inductive, right? It's a positive value. And notice that as you start to increase your speed, the motor starts to accelerate or increase speed. That basically it stays fairly flat here, and then it kind of comes up really high up here. Now we're not operating in this range. We're going to be operating in this range here. So let's go in and let's expand this. All right. Now let's look at this. Now what I have here is this is a slip. This vertical line corresponds to a slip of 0.02, which is what the example in the book used. Here's a slip of 0.03, and here's a slip of 0.04. All right, so the green line here corresponds to Z in magnitude, and the red dashed line corresponds to the angle. So let's look at 0.2, a slip of 0.2. So for here, what we've got is the magnitude is about 7. Somewhere around 7 ohms. Okay, and the phase angle here is somewhere around 32 degrees. Okay, if we go, and then we can see that right up here, these are the values that actually come from this, right? So for 0.02, the magnitude about 6.7, what I said, about 32. And then real on that. We haven't plotted that yet, but we will next. And then notice that as your slip increases to 0.3, then you go from 6.7 down to about 4.9 or about 0.5. Okay, and your angle has gone from 32 up to 26. 32 down to 26. And then when we go to a slip of 4, then here what we have is we have close to 4 ohms here, and we have about 24 degrees here. Okay? So, and then here's the synchronous speed, but we're operating somewhere around this. So that's the actual input impedance seen from the stator and input terms. This is what the AC line voltage, the 3 phases that are applied to it, see. Okay, let's go back, and this time let's look at a different plot. So this is what this feature is such a great feature. I love this of Python. I go to here, instead of commenting out everything individually, I'm going to go here and I'm going to comment out that region. Okay, and now what I'm going to do is I'm going to go in and I'm going to uncomment this, uncomment the region. All right, and now let's plot. Okay, now this is the real part and the imaginary part, and let's go here and notice that these are really, really low here. Zn imaginary pretty slow and real. Let's zoom in here. Now look at the real part here. So the real part here, and we can look at here at slip of 0.2, the real part is 5.72, okay, here. And then the angle here, imaginary, well not the angle, but the imaginary part is about 3.6. And notice here again, what we're seeing is that as you increase more slip, then you get a change in impedance. The impedance is dropping down, okay? The angle is basically going down, and this is going down, all right? And notice that if you get even higher, like 0.08, what you got is you got the input impedance here, the real part, is basically close to 2, and the angle here is around, not the angle, but the imaginary part is maybe around 1 or so, somewhere around there. Okay. Okay, so there you go. There's impedance. All right, so let's close this out, and let's go back. So let me close this out here. All right, and what I'm going to do is close this out here for right now. Okay, let's go back in again. All right, and so that was the impedance. Let's go to the next thing. So that was input impedance. Let's go to the current. Okay, now what we want to do is we want to figure out what the current is. When I was first going through and looking at this stuff, I found a graph that they had in the Kingsley book, but I didn't really find a lot of stuff online, you know, and that kind of motivated me to go in and try to do some calculations, because when you first turn on the motor, it's really high current going in, and that's what kind of got me into these motors looking a little bit deeper, is where is that current coming from? Why is it so high? So let's go in and let's do some calculations here. So the first thing is let's go to this, and we know what Zn is. So really what we want to do is we want to figure out, well, okay, what is the input current in here as a function of Zn, okay? And we already found Zn, and so let's assume that this voltage here as a phase angle of 0. This will be our reference, so it's magnitude at this angle, okay? So we can calculate this in Python real easy. We don't really need to do anything else. We can also find IR by doing a mesh analysis, okay? Now, with the mesh analysis, you write the loop equation of this and loop equation here, but we already know what IS is, or we will once we calculate this, so we don't really need to do that, which saves us a lot of time. All we need to do is write a mesh equation here for IR, and we already know what IS is, and then we can calculate it using Python. So mesh 2, what I did is wrote a loop here. So what we have is we have IS, this is going this way, minus j omega Lm. And then we have IR, which is going the opposite direction, so this would be plus j omega Lm. And then we got IR times j omega Lr. And then we got IR times this. Okay? So if we solve for IR, we get IR is equal to this divided by this, right? So it's IS j omega Lm divided by j omega Lm plus Lr plus RR over R. Now here again over S. Here again, I wanted to get the 1 over S term out. You know, if I was doing this by hand, then I'd probably want to leave that term because that's an important term. They work together. But seeing as I'm just plotting it using tools that make life much easier, then let's get rid of this 1 over S. So I'm going to multiply the bottom by S and the top by S. And so what I'll get is JSW, or omega Lm IS. Then SW times this plus this. Okay. Alright, so there's IR. And we've already got IS because we're going to calculate that in Python. Now note that this IR here, this IR squared times this term here gives us the total power transferred from the stator to the rotor. Okay, mechanical plus losses within the rotor. And so here, since RS over R equals here, then the actual, this is lossy power, this is actually the motor power that's actually going out. Then I squared R times this term here, okay, or times this whole thing will give, this will be the total power transferred, I squared R times that, or IR squared. And then this times this will be losses due to the rotor. And then this right here will be power converted to mechanical rotation. And also this power is used to overcome frictional forces, bearings, and things like that. Okay, so that looks pretty good. And it looks like time is up again. So let's go ahead and stop right here. And in the next video, what we'll do is we'll go in and do some plots. Okay, so see you in part 3.